Just let me quickly open the data booklet. Has 2 pages on which you have all these bond energies. We can have a look at them. Okay, so it's probably in the beginning over here. So there are two types of bond energies given. The bond energies given for diatomic molecules. Uh, Homonuclear means homonuclear simply means that these are bonds formed between the same type of atoms, like HH, N triple bond N. D over here is, remember, deuterium. Deuterium is an isotope of hydrogen. Now you don't have to memorize the values. This data sheet would be given to you. ठीक है, Sanjeeda, the data booklet is going to be with you at all times. So you don't have to memorize any of the values. Anyways, so just going through the data booklet, I'll just explain two things. Homonuclear means, uh, and remember, these are diatomic molecules. Diatomic means that the molecule consists of only two atoms. So, and remember, these are for gaseous substances. Defined for, if the bond energy for iodine is defined for iodine being in gaseous state. And heteronuclear means that it's a diatomic molecule, but the atoms are different. I mean, they're different, like fluorine and hydrogen, chlorine and hydrogen. So there are different types of atoms, bonds between different types of atoms. But it doesn't really matter. Ignore heteronuclear or homonuclear. And there's going to be another page, probably below this. And this is for polyatomic molecules. These are large molecules. Now the problem with large molecules is they've said that these are average values, because if a molecule is very large, then it has all sorts of things happening to it. So for example, if you have a molecule, like, I'll give you an example. If I have a methanol molecule or an ethanol molecule, well, let me draw a methanol molecule. Now bonds between polyatomic molecules, which are larger molecules, they're not exactly identical. For example, if I have a carboxylic acid on one side, now if I highlight this bond, this particular ONH bond in both groups, in both molecules, they are almost identical. But since the other atoms have some sort of effect, so the bond, I mean, the strength of the bond would be different. For example, this is a carboxylic acid. If you remember carboxylic acids are strong acids, which basically means that in a carboxylic acid, the H breaks away very easily. I mean, this hydrogen over here, it breaks off very easily. So the problem with polyatomic molecules is that each polyatomic molecules and their bonds are going to be slightly different from another polyatomic molecule. An OH bond in methanol is going to be different from an OH bond in a carboxylic acid. So they're not going to have exactly the same value. Uh, there would be slight variations, but we are ignoring variations, and instead, what they have done is they've given us the average values. Okay, so for example, the C single bond C in any molecule, it's not going to have exactly the same value. There's going to be variation. Sometimes it's going to be a weak carbon-carbon bond. Sometimes it's going to be a strong carbon-carbon bond. When we study chemical bonding, we'll discuss these variations as well. Similarly, carbon, double bond carbon, not all of them are going to be exactly identical. It depends on the molecule. So all these bonds are part of a polyatomic molecule. So you can at best just use average values, because every time a molecule is different, the bond energy would be slightly different as well. So these are all the bonds in polyatomic molecules and their average values. For example, even look at the carbon double bond oxygen. Usually it's 740, around 740, but if it's in carbon dioxide, it's around 805. So even over here, they've actually listed, because there's a huge difference in the bonds, especially for C double bond O. If it's part of the carbon dioxide structure, there's a huge difference in the value. So be careful with this. So anyways, we're going to use these average values that are provided to us, and we're going to try and solve this question. Not this question. Okay, let's rub this off. Uh, Let me quickly. Just remember, for polyatomic molecules, not all values are going to be exactly the same. Anyway, so starting, and we're going to try and solve this. So you have to break 4 CH bonds and you have to break 1 CL bond. So go and look at the data booklet and try and find out what the value is for CH bonds. So CH over here, this is CH given. Take it right at the top. The value that's given, the average value is 410. So we're going to put that, place that over here. That's 4 times 410. You would have to break, and this is going to be your positive values, endothermic. And then you have to break the CL bond. Go and have a look. This is a diatomic molecule. So the CL bond would be on the other page, which is here. You can have a look at the CL bond. It's given as 240. It's given as 242. So that's plus 242. And the other values, they would be all exothermic. Bond formation is exothermic. So you're forming 3 CH bonds. The value is already with you, 3 into 410. Then you have a CCl bond that's being formed. So have a look at the data booklet again and try and find the C. Where's the CCl bond over here? So it's given as it's given over here as 340. So we're going to use that minus 340, and you're only forming one bond. And there's one HCl bond that's being formed as well. So have a look at HCl, which is again a diatomic molecule. So I'm going to look over here. This is given as 431. So this value is provided and it's 431. So just remember, bond breaking values are all going to be positive. They're all going to be endothermic. So add positive signs to them. And bond formation values, they're all going to be negative. And you have to be very careful. This is one of the places where everyone makes, remember, in all energetics questions, there's room for a lot of silly mistakes, especially in counting the number of bonds. Make one small error and the whole answer is going to be incorrect. Um, so even when you bring in your calculator and you start calculating these values, you have to be very careful with this. Okay, so very carefully do your calculations. So it's going to be 4 into 410 plus this 242. Then it's minus 3 times 410. And then there is minus 340. And then there's minus 431. Okay, so I'm getting minus 119. So my overall enthalpy change for this reaction, the delta H that I'm going to get is going to be minus 119. And remember the units, it's kilojoules per mole. Always enthalpy change units are going to be kilojoules per mole. Why? Because if you have a look at the data booklet, the unit for energy over here that's given, it's given as kilojoules per mole. So your values and your answer is going to be in kilojoules per mole. So that's going to be your answer. Rida, Sanjita, is this clear? Okay, so we're going to jump to solving. We're going to try and solve some past paper questions related to bond energy now. Okay, now let me just quickly. So all these questions are related to bond energy. Starting with the first question. The question is simply, uh, it's asking which reactions are exothermic. Now, the first tricky part is you have to figure out. I mean, you must be familiar with the structures of these substances, like which bonds are broken and which bonds are formed. So we need to figure out the first reaction. There's an O and H molecule. So it's going to be a single bond because hydrogen always forms a single bond. Ignore the dot for now. We're going to discuss what the dot is later on, much later on. Just ignore it for this question. Then you have, so that bond needs to be broken. And what else? You have an HBr molecule, so that bond also needs to go. These need to be broken. Find out what the energy is for OH and for HBr. Open the data booklet. So let's quickly open the data booklet. OH is going to be, I can't find it here. Uh, OH must be, I mean, this is where OH is. It's given as 460. So that's the value. So OH is 460, and that's obviously plus because you're breaking that bond. And HBr is, we need to find HBr as well. So that must be on the previous page. HBr is given over here. This is given as 366. So use that value. So it's plus 366. So how many bonds are formed? You have an H2 bond that's being formed. So that's a single HH bond. Have a look how much energy is released when it is formed. And that's given over here. That's 436. So that's provided. And you're going to write minus 436 because it's going to be exothermic. And how many, and there's a Br and O bond that's formed. Now Br is group 7, so that also forms a single bond. The bond energy for Br is already provided over here. That's going to be minus 235. Open your calculators quickly and try and TK, you have to be very careful with your calculations. It's going to be 460 plus 366, and then it's going to be minus 436 and minus 235, and that gives me 155. So that means the first one is actually coming out to be plus 155 kilojoules per mole, which means that the first one is definitely, so that means that the first one is definitely not, it's not exothermic. And I told you that in 1, 2, 3 type questions, if the first one is wrong, the second and the third are definitely going to be correct. We can have a look actually. Let's look at this one. Uh, we'll try number 3. Over here, you're not, you don't need to break any bond. There's a single hydrogen atom, so there are no bonds over here. You need to break the HBr bond. So that energy is given as plus 366. This is given over here. And how many bonds need to be formed? There's a single bromine atom, so nothing has to be formed over here. An HH bond needs to be formed. So that is given over here, it's minus 436. So if you sum this up, your overall enthalpy change would be plus 366 minus 436. So it's going to be plus 366 minus 436, and that gives me minus 70. So that comes out to be minus 70. So these two are definitely correct. Let's have another one. We can ignore number 6 for now. We'll just focus on these questions. Here's another question, and the table is given in front of you. So using average bond enthalpies in the data, what is the enthalpy change of combustion of ethane? So break all the bonds and form new bonds. Now be very careful how many bonds you're breaking. Over here, it's count the bonds. There's a carbon hydrogen bond over here and another carbon hydrogen bond over here. So carbon and hydrogen bonds, you would have to break 2 of them. The previous one, question number 6. ठीक है, we'll do this. ये पहले कर लेते हैं. So if we look at this question, ignore what free radical substitution is. The question is, which reaction has the lowest activation energy? ठीक है, the only reason I wasn't doing this question was that we hadn't done activation energy. But I'll explain this question. Activation energy is the energy that is needed to start a reaction or initially. So it's the energy needed at the beginning, at the start. Why do you need energy at the start of a reaction or at the start of any reaction? Okay, why doesn't your match, there's oxygen in the air, why doesn't it burn on its own? Why doesn't wood burn on its own? Why do you need to heat it uh, before the reaction starts? The reason is every reaction, what is the first step? You have to break the old bonds. Where's our notes? Just 1 second. So activation energy, the first step usually involves bond breaking, and that requires energy. So unless the old bonds are broken, new bonds cannot form. So sometimes the activation energy is very high. The bonds that need to be broken are very very strong, which is why the reaction doesn't really start. And I mean, this is one of the reasons why nitrogen in the air is inert, because the bond between an N2 molecule is a triple bond, and that's a very strong bond. So it's very hard to break that. So new bond formation doesn't take place because the old bonds haven't been broken. So activation energy is the energy that is needed at the start of reaction to break the old bonds every time. So if the old bonds are very very strong, then the reaction would require a very large amount of energy. And if the old bonds are very weak, then the reaction would happen at a much faster rate, because it would be easier to break the old bonds and new bonds would be formed. Now, if we go back to our question, the question says which one has the lowest activation energy. So the energy needed at the start to break bonds, this has to be minimum. Lowest activation energy is that energy needed at the start of the reaction to break the bonds has to be minimum. Uh, so if you look over here, in this reaction, if you look at the reaction carefully, you would have to break the ClCl bond. So, I mean, there would be energy needed at the start of the reaction because you have to break the ClCl bond. So I'm going to write it over here that in this first reaction, I mean, you can have a look at the data booklet. ClCl bond needs to be broken. So it needs to be broken in this case. We can check the energy that is needed for that from the data booklet. Look at the second reaction. If you look at the second reaction, you would notice, and let me write this reaction C2H6. It's Cl reacting with C2H6. So there's two carbons with six hydrogens. And on the other side, it's C2H5 that's being formed. And an HCl molecule that's being formed. Okay, so it's written over here. Now, if you look at this reaction carefully, even I say even in this reaction, you would have to get rid of this bond. The carbon is making a bond with CH. So in this entire reaction, one of the CH bonds has been broken. Only then would this H then go and bond with the Cl. I mean, there was an H over here, and that H went and bonded with the Cl over here. So at the start of the reaction, the CH bond has to be broken in this reaction. So some energy would be needed to break that. We can look at the data booklet and have a look and find the value. I said, look at this third reaction. If you look at this reaction, now it's clearly obvious that previously there were two chlorine atoms that were bonded together, but now there's a single chlorine. So that means right at the beginning, this ClCl bond was broken. So there would be some energy that would be needed to break the ClCl bond. But if you look at this last reaction, have a look at this last reaction, number D. What you would notice is that there's a single Cl atom and there's a C2H5 molecule. So this is C2H5. And what the product is that the two get together. So there's C2H5 and the Cl, they just simply combine to form this C2H5Cl molecule. So in this reaction, not a single bond has been broken. Now this indicates that there would be absolutely no energy that would be needed at the start to break the bonds, because in this entire reaction you're not breaking a single bond. ठीक है, कहीं पे भी not not a single bond has been broken for this reaction to happen. So if no bond is being broken, that means no energy is needed at the start of the reaction. So hence answer D would be the correct answer. This would have the least activation energy out of all the four. It's going to have the least activation energy out of all the four reactions. Is this clear to everyone? This question, yes or no? Just remember, we're going to come to activation energy later on as well. Just remember this fact that activation energy is simply the energy that is initially needed to break the bonds. So if a reaction you don't have to break the bonds, then it's going to have very less activation energy. Now coming back to this question, you have to figure out the enthalpy change of this reaction. So you have to be very careful in counting the bonds that would be broken. So break all the old bonds and then form all the new bonds. So carbon and hydrogen bonds, there are two of them. Then there's a carbon and carbon triple bond in the middle. Okay, so there's a carbon and there's only one of them. Then there are 2.5 oxygen double bond oxygens that need to be broken. So there's an oxygen-oxygen double bond, and you have 2.5 molecules. So you have to break 2.5 oxygen double bond oxygens. All of these bond breaking would be endothermic. And the values are given in front of you. So this is plus 410, and that's into 2. The other one is C triple bond C is 840, and that would be multiplied by 1. You're just breaking one triple bond, and oxygen double bond oxygen, that's also given. That's given over here as 496. So that would be 496 multiplied by 2.5. And all these values are going to be positive. And then how many bonds are formed? Now, be very careful. Always try and draw the structure. This is a water molecule. This over here is a carbon dioxide molecule. And you have exactly two carbon dioxide molecules. So count the bonds that need to be formed. The OH bond, if you look carefully, that's two of them. Okay, count the bonds. There's an OH bond over here and an OH bond over here. There's a carbon double bond oxygen bond, and there are two of them as well. And there are two molecules, so that's another two. So that's a total of 4. You basically have to form. You basically have to form 4. In one molecule, there's a carbon double bond oxygen, another carbon double bond oxygen. So in one molecule, you have to form 2. So in two molecules, you would have to form 4. You can get these values over here as well. OH is going to be 460. So these would be negative. It's going to be minus 460. Bond formation is negative. Carbon double bond oxygen would be given somewhere at 740. So use that. So these are my values. And sum all of them up. It's bond breaking, positive, minus bond formation, that's negative. So we're going to try and sum them up. Let's start. It's going to be 410 into 2 plus, be very careful with your calculations, plus there's 496, start 2.5, and then there's going to be all the minus values, minus 460, but that's going to be times minus 460 times 2, and then there's minus 740 times 4. That gives me minus 980. So my overall value is going to be minus 980 for this particular reaction, which is given as A over here. So these are all very simple questions that need to be solved. It's the same formula over and over again. Now, Acha, is this clear? The last question, yes or no? Is this clear? So moving on, there might be tricky questions like this. Now, this one is a tricky question. He's saying which process could be used to calculate the bond energy. So he's asking you to calculate the bond energy of the covalent bond XY. So the bond energy of the covalent bond XY needs to be calculated. And he says you have to calculate the bond energy of the covalent bond XY by dividing delta H by N. So the bond energy of the covalent bond XY is calculated by dividing delta H by N? I mean, that's the question. Okay, the question is that in all these processes, if you try and calculate the bond energy for the covalent bond XY, you have to do that by dividing delta H by N. So you need to somehow get this expression. And we just know one formula, which is that enthalpy change is bond broken minus bond formed. Now I'm going to go through this one by one. Okay, I'm looking for this expression. Which process out of A, B, C, and D would give me this particular expression? I said, let's look at the first reaction. And I'm going to just quickly tell you that's also your answer as well for this question. Uh, Now, how many bonds do you think have been broken in this reaction? And how many bonds do you think have been formed in this reaction? Now because it's given in this form, XYN, and there's X and N Y atoms, right? Now, because it's kind of given in this X and Y, uh, I mean, it's given in X and Y, and there's an N over here, so it's harder to figure out how many bonds are being broken and how many bonds are being formed. So what I'm going to do is I'm going to put a reaction, a real reaction, which would be very similar to this. So think of N being this 4 over here. Think of X being as carbon. Think of Y as being a hydrogen. What we are doing is, uh, if I break all the CH4 bonds, I would get one carbon and I'm going to get 4 hydrogen atoms. Okay, so the whole question is, what did I do in this reaction? How many bonds did I break and how many bonds did I form? So I broke 4 CH bonds were broken. I mean, that's endothermic. Okay, this is going to be energy would be needed to break these bonds. How many bonds did I form? I did not form any bonds. I mean, there's a single carbon atom and there are 4 separate hydrogen atoms. So no bonds formed. Right? I hope this is clear to everyone. Right? Yes or no? If this part is clear, the CH4 part. Okay, I've written an equation. There's CH4, and I've broken all the bonds in between carbon and hydrogen. I get one carbon atom and 4 hydrogen atoms. So I'm not forming any bonds. The only thing I've done is I've broken 4 CH bonds. Now compare this reaction with this XY reaction. I mean, these two are exactly the same. Uh, so it's very obvious that XY were bonded together first. Okay, they're exactly identical. Like you can put N, substitute N with 4, and you get the same reaction. It's going to be 4Y over here. Now, based on this analogy, how many bonds am I breaking? I'm breaking XY bonds, and how many of them I'm breaking N bonds of XY? And how many bonds am I forming? I'm forming no bonds. I mean, no bonds have been formed between Y and X. I mean, so in the product side, there are no bonds being formed. So the entire reaction is that I'm breaking these many bonds, N bonds of XY. So what was the formula for calculating enthalpy change using bond energies? The formula was the enthalpy change is basically bond breaking. I mean, that's endothermic, that's positive, and minus bond formation, right? This was the formula for enthalpy change. So in this particular reaction, the formula for enthalpy change would be, so the formula for enthalpy change would be that I need to break XY bonds, N of them. So it would be bond energy of XY, and it's going to be multiplied by N times, because I have to break N bonds of XY. Exactly in the same way over here, I had to break 4 bonds of C and H. Now over here, I have to break N bonds of XY. And how many bonds do I need to form? There's 0 bonds that are being formed. So that's 0. That's nothing. So look at my expression. My overall enthalpy expression is going to be that if I try and calculate the enthalpy change for this particular reaction, it's going to be n times the bond energy of xy, and no bonds are being formed, so that's 0. And if I rearrange this, the xy bond energy, how do I rearrange this, get the n to the other side? And that gives me the same expression that they were looking for, which is that the xy bond energy is basically the enthalpy change of the reaction divided by n. Is this question understood or not? Yes or no? Okay, is this clear? So just, I mean, this was one of the difficult questions. Not a lot of people were able to do this question. Uh, why are the other ones wrong? Because in the other ones, you would need YY bond energy. Look over here. You have to form the YY bonds. Uh, so that bond energy would be needed. Same over here as well. Y and Y bond energy would be needed. Over here, the number of bonds that are being formed would not be n, because XY bonds have already been formed. You're just making one more XY bond. Like n could be 5, so that means 5 XY bonds have been formed. Over here, n minus 1 could be 5, n would be 6. So it's not going to be n times XY bond energy. So all the other ones, these two are definitely wrong because they need YY bond energy as well. Y2 molecule is being formed. So you need the bond energy of Y and Y between the YY bonds to figure out the enthalpy change. Tanika, we'll start. We'll continue with this. We'll try and see if there are more questions that need. Most of the other questions are very simple, relatively simple. ठीक है. Tomorrow we'll hopefully move towards Hess law, and we'll try and draw. That part is going to be difficult. ठीक है. Most of these questions are going to be relatively very easy. चलिए ठीक है. Okay, take care. Allah Hafiz.